Okay, we're just continuing with the lectures from week 3. So I'm picking back up where I left off, and I'm just going to make my screen so you can see it now. There we go. I hope most of you recognize this. It's from the classic Nintendo game Super Mario Brothers. Why am I showing you a picture of Super Mario Brothers? Well, one of your assignments this week has a Mario theme. I think it was actually from last week, but we'll come back to that theme a few times, just as a metaphor for the visual display of information using computer programming languages. There's a part in your notes this week that that uses maybe this visual metaphor I'll point out of the circled blocks here. And the visual metaphor is some unit that's repeated 3 times vertically. And just to remind you, I'm not going to pause and do live coding during the stream here for the lectures. And note that we don't promise any videos for either for the lecture parts or for the notes or for the tutorials. But the notes especially, and this is the notes page up here. You can see that you could get to where I am by coming to the schedule, going to the notes for week 3, and then I was on the arrays section. Debugging actually was on the section I was. It's your responsibility to go through these notes before class every time. Thing I'm not going to do in lectures, but most of the time, if I do go through slides like I'm doing this time, is I'm probably not going to stop to do live coding. But it's very important for you to do so. So when I go back to my slide, I'm really prompting you here to check out those notes, pause this video, and go and read carefully through the notes, type in the code that is suggested, and run it and see it for yourself. This is just a reminder to use that method we introduced in class, the rubber duck debugging. So I'm just going to mention that again here to, if you get stuck, you can ask questions of the duck. You can ask and discuss the material with each other, which I strongly encourage. You can use AI as well, with those caveats that we've covered several times now, that you mustn't use it to produce code or explicitly answer questions for assessments. But, you can interact with it to evaluate what code is doing, or if you're getting a problem. That's acceptable. What we're going to talk about now is data types and how they're stored in memory, and different kinds of structures that we can use that utilize these types. And we're going to introduce eventually the concept of arrays. So we've talked about some of these variable types. One of the tutorial videos I made talked about booleans, zeros and ones, integers, they're non-decimal numbers like 1, 2, 3, negative 1, 2, 3, long integers, which is a bigger magnitude of integer than a plain old integer, twice as much memory. The floating point, which is decimal numbers like 2.5. Decimal accuracy determines the size of the storage that's needed. A double is a double accuracy float. Character is a single character, could be a special character, or A, B, C, D, E, capitals and lowercase. And a string, which is more than one character in double quotes. And there are others. These are the fundamental ones. Note that each of these contains some level of memory storage that's attributed to them. So the Boolean is 1 byte. Now you might be thinking, gosh, a Boolean is just a 0 or 1, and 1 bit can contain a Boolean because 1 bit can represent 0 or 1. And nevertheless, we reserve 1 whole byte to represent the Boolean in C. The integer is 4 bytes, long is 8 bytes. Float and double are 4 and 8 bytes respectively. Character is just a single byte. And then string, the number of bytes is determined by how long the string is. You could just have a word, you could have a sentence, you could have a whole book. So when we're thinking about this, one of the things that the C programming language is designed to account for is memory. What is this? Does anybody know what this is? Well, I already said it. This is a memory module, a RAM stick. Some of you may have seen these before. If you've built computers, or if you've opened up your computer box or your laptop, some of you may have never seen this before. But you'll have this in your laptop, in your PC, in your Mac notebook, in your phone, in your smartwatch. There'll be some kind of storage structure for memory. And all this is a circuit board and little gold wires printed onto the board. And they are just that, they're wires. We have some contacts. This one is designed to go into a slot with a wide section and a shorter section over to the left. And then, on the board itself, we have little chips all over the place, and we have these conspicuous big ones. Now, I'm tempted to say that this could be a 16 gig RAM stick, but I don't think it is. I think this is an older one, and it's just a coincidence that this is a 4G. I don't know. Each of these modules will store some amount of information, and the whole point of this is that these chips store electrical charges in different locations. We're going to just talk about that a little bit to get the idea of what it means when we're declaring a variable of a certain type, and we're in doing so we're asking the computer to reserve a little bit of memory for us. What does that actually mean? Well, you can think of each of these. Chips like this as having addresses on them. And, if we look at it up close, we can actually focus each one of these chips. There's several on each board, and there's all this other stuff going on. But if we just focus on that one chip, we could actually divide it into quadrants. And we could think of each quadrant as a little space where some bits and bytes, for example, for a variable we've declared, might live. And let's say that we start off, we don't have anything, we haven't asked for any space on the computer, so everything's blank. But maybe we ask for 1 byte of storage for one of our bytes. Well, we start filling up these little storage places one at a time, and we can fill blocks of them sequentially. When we have nothing in storage, it does just that. It stores them sequentially, and we can reuse this RAM. I use that acronym RAM. What does it stand for? Do you guys know? Have you heard that it stands for Random Access Memory? Now, this isn't a computer hardware or computer systems module, and we probably won't even cover this in the course, but it's very relevant to talk about, so we're just going to briefly talk about it now. Let's get rid of that background so we can start thinking about how memory works when we reserve space for variables. Let's zoom in a bit. We can do this, and let's say that we want to reserve some integers. Let's say that we want to reserve maybe for some different problem sets, and maybe the grades that you earn on the problem set, you get a 72%, a 73%, and maybe one you didn't do so well on, you only got 33%. Okay, so these are our three integers, or scores for our assessment. Well, what if we wanted to do some statistics for this? What if we wanted to maybe calculate the mean to keep track of what our grade is, or in a running tally, what we could do, oh, and by the way, if you're following along with the code, you can check this out in the code zips, and you should run it yourself. It's in the scores files. This is score0.c. So what would this look like? So we've got three variables. We've got three integers. We've got 72, 73, and 33 for values. Maybe if we scored 1, and if I just back up several slides, I'm going to back up lots of slides to this one. The int, remember, is 4 bytes. So if we just go back to this, we've taken up, if each one of these squares represents a byte, with score 1, we've sucked up 4 of the squares, 73 and 33, likewise. Well, this fits just perfectly. Not just the numbers, but what we're doing is actually scoring the values. And if you were to look in the binary code and remember back to that first lecture when we talked about this, the first set of notes, you could calculate that this is 72, this adds up to 73, and this adds up to 33. Okay, so if we think about this code where we sequentially write these lines, it works perfectly fine. But actually, there's a bit of a problem with it. You could think about what the problem might be. It's a bit of a problem to do with one, the efficiency of this code. Now, what if we wanted to add to the scores? We have 10 problem sets in this module. What if we wanted to calculate our score after the fourth one? Well, we could do that. So it's not very efficient, but we could add a new line and add a new integer and add a fourth score, and maybe we did a little bit better on the fourth one and got a 65, semicolon. We could keep doing that. We could add as many as we wanted, but it's not that efficient, and it also creates more code, so it puts a burden, makes your program bigger. It makes it harder to read for your future self or somebody else. Also, a second problem is we're using this concept of kind of magic numbers in a way. I introduced that in one of the tutorial videos, and you probably encountered it in the notes if you went through the week 2 notes. But this idea of magic numbers, this is something you hard code into your code that otherwise doesn't make any sense and isn't flexible. And, a problem is if we hard code this in, it might not make sense to other people, but also what if we made a mistake? We've got to hunt back through our code and change the hard code, recompile, run it again. So these are some issues with this kind of code. Well, there's a solution to this that solves some of these problems. And the solution is a data structure that we're going to extensively use, and it's called the array. So what arrays do is, you can think of an array like a street. And let's say this is just a street in a neighborhood. And let's say there are some houses on the street. And this is kind of the metaphor that I think of, that I learned as a student, that has stayed with me my whole career, actually. So if we have a street and we have some houses on the street, maybe in the houses live our numbers. In this case, 72, 73, and 33. And how do we find the house to get the number out of the house? Well, houses have addresses, and arrays, like streets, have addresses. And C, that starts with 1, starts with 0. I'm just going to, might as well use my eraser here. Boom, there we go. I was trying to draw that with my with my mouse, which is notoriously difficult. So I'll try it with the pen now, and that's much better. So what we can do with an array is it's like a little container that we put different types of values in. Now, one thing about an array is these are integer values, and if we create an integer array, every value that's stored, the only possible value to store it if we create an integer array will be integers. If we need floats, we would create a float array. And likewise, we always start at 0, at least in the C programming language, and each address in the array is addressed sequentially, 1, 2, 3, and so forth. So what this would look like if we declared an array is we'd use the identifier int. We would declare the name of the array, scores, and we'd use this little notation, the square brackets, to indicate that it's not just an integer, this is an array of integers. And then finally we put the number inside the brackets that indicates how big the array must be, how many addresses are stored in it. So in this case we need 3. We have 3 scores to start with anyway. And remember, this is a little thing, you'll get used to it, but it sometimes takes adjusting, is that even though we have 3, we don't go up to 3, 1, 2, 3. We start at 0, and so the 3 indicates 0, 1, and 2 for the addresses. Now, the way we get it, the values that are contained in scores, are we use the address inside the square bracket and assign the value to that address. And that's the way we both assign the values and retrieve the values. So score 0, here we're putting 27 inside the box at the address scores 0. And if we print the value of scores brackets 0, we would get 72. So it goes both ways. So the way that the memory structure would look for an array is that it takes up exactly the same amount of memory. It reserves 1 block, 4 bytes of space for each of those integer values. The difference is the way we get at the values. And it's kind of efficient because we're reusing the name scores. We're indexing them by the address. The fact that the address is sequential as an integer is super useful. You can imagine, I'm just going to say it verbally, but I'll let you go through the notes and run the code yourself. We're going to develop in the notes, and you should run this, a loop that accesses with a variable, say a variable called I, or another kind of counter variable that sequentially goes through and cycles through the consecutive values of the addresses. That's the whole point. Now, we can do this with any type of array. We can have set up an array, a character array. Here we've set up 3 different character variables. We've set the first one, C1, to H, second one to I, and the third one to an exclamation point, hi. Have our memory. Memory takes just 1 byte for a character kind of variable. So the storage would look like this. We could put characters in there for numbers. This is analogous to our numbers one. And, we've got our bytes in there to represent those numbers. So strings as well. We've talked about this a little bit. We can set a string variable to several characters. And in this case, we'll set it to the same values, hi. And here, the structure is a little bit different. Rather than having discrete storage values, we've by storing a character string of 3 spaces, what we do is we have 1 unit in memory that takes up 3 bytes, because we've reserved 3 bytes by implication by having 3 characters in our string. Of course, because that's a string array, we can access those by the address again, and likewise we can print them by the indexed address. That's pretty neat. And there's another thing, is if we have only asked for 3 spaces, we'll only reserve and use 3 spaces in memory. And by default, if we add some spaces that don't have values, it's not that there's the absence of information in that. By having an extra space, by calling an extra space, we take up the memory in the extra space, and the default is an empty byte, a byte that represents 0. And, we could explicitly call it 0 with the escape character in programs. Again, this is something I've covered in tutorials and the notes. So oftentimes we may want an escape character at the end of a character string just to have a hard stop to indicate that that's the end of our character string. So this is just a convention. And, that's a null space. Okay, and it's very convenient if you're looking in solving memory problems, or, if we're doing something a little more on the computer engineering side rather than the coding and data science side, to indicate that a string is stopping, especially when you have a body of text, and that's the null value. Okay, remember back to the ASCII table. We encountered this in the first week of class, and remember that we have some kind of values that align to certain special values. The ones that we looked at in class were codes for letters and numbers and symbols. Of course, these numbers aren't technically considered numbers. They're considered the characters representing a number. And then we have the numerical code that represents them. So we covered this in the first week. You want to go back and refresh yourself if you don't quite remember that. But we have these special codes over here in some of these values. So the 0 represents the null. So let's think about strings in terms of arrays. So let's say we declare a string S as high and string T as by, and we've got some memory here. We're going to block off the character string high with our null character. It takes up 4 bytes. We're going to block off by with an escape string. It blocks off 5 bytes. And we can access these with the indices for our arrays, if we construe this as an array. And we can expand this idea to all sorts of types. The way it would look for character strings is we declare a string for an array. And it's an array, let's call it words, an array with 2 addresses, high and by. So the way we get at those is exactly the same way as other character types. And so now the only change is, the way we designate the address of those bytes. Now there's a funny thing with character strings, is that because strings themselves can be accessed with array indices like we just talked about, when we formally declare an array for one of words, we actually are declaring a 2-dimensional array implicitly. So it's this is a new bit of information that arrays can take on many, many dimensions. I mean, it's very easy to think about one dimension. The metaphor I gave was that of a linear street with addresses along it. But if we have a two-dimensional array, like the one that's implied up here, all that means, this is still quite easy to think about. It means there's another street, and there are more addresses. Of course, the addresses don't just run along the street. This runs like a matrix, we might call, or a two-dimensional array. And each one of these, if we think of these, by these I mean, just going to circle that. This is a column, and we think of these as the rows. Then these addresses start to make sense. So if we wanted to access this address, we would number the columns 0, 1. Let me get my pen. Drawing with my mouse is just not working. And then 0, 1, and 2. What we could see is that if we go by rows and columns, then this unit would be words two for the second row, and column 3. Okay, so that's how these addresses work. And you can see for the first word, it's the first dimension of this array, we're starting at 0 for high and the null. And then for by, it clicks over to the next column or the next row. Okay, so to get functionality for handling strings like this, we need the string header, and you can just kind of check out. Actually, I strongly recommend that you check out the manual for the different headers and the different functions that we use, and you can just search for them on the manual page here. And if you click on this link or just type in this link, it'll take you straight to the string.h, and it'll tell you a little bit of extra information. One of the interesting functions that we can get in there is string length, strlen. And what you can do, if you want to check out the code, you can look at the notes, and you can look at the length scripts, and maybe look at length2.c, and you can see the syntax that's going into this. We also have type.h, ctype.h. So it's some functions that will have some utility functions for different types. Again, you'll need to look through the notes, and I encourage you to run the script. And there's a help page for this. Do check it out. It's important so that you know what's going on. Okay, the ASCII chart. We can kind of look at the high and by numerically, the high and by numbers. So check out the code for that. Now, I did a tutorial video last week for some command line arguments, and I'm just going to verbally go through them now. Again, I'm not promising videos for every tutorial, but I may make another one for some command line arguments. But we go over this. If you watch the first video and you go through the notes, I strongly encourage you. You'll be much better off if you run these yourself and experiment with them. Play with them, make mistakes, learn to type them, see what they do. You really can't mess anything up in your repos, especially in the sandbox. And the ones we talked about before, the ones we've already been using for the assessments are ones like make, cd to change directory, make to compile, go through the compilation process, etc., ls for list. So we've looked at these before. Now, we are looking here at the structure of almost every program you'll write will include the header standard IO. A thing that every program also will usually have is a main function. And one of the ones that we've used a lot, one of the patterns here is, where we're not returning or submitting anything to the function in the way of an argument. So we have void as the argument, and we're setting main to int. Could have a void main as well, but there's stuff in here. The 3 dots represent stuff. So we've got void because we're not adding anything, but we could have some stuff. And our programs now it's going to be important for us to start adding arguments to increase the functionality of our programs. So for example, we could have an integer for some argument that we pass to the main function. And we could have, for example, a string that we pass in the form of an array. So the arguments could be any type, and they can be arrays and other kinds of structures that are passed, by the user. And they can come in different ways. We're going to, we're working on the command line here. So we're going to think about this. Now, if you go to the notes, what you'll see is a program that starts to talk about how to program using strings with a function like this, and it goes through the development of a program that stores strings as arrays, and you're going to want to go and run that code and read the notes. Now, I think I'm going to end this video here. It's long enough, and I'll come back and I'll just finish up in another video. So that's all that I have to say about that.